Let me begin with another topic here. That is the effect of signal characteristics on the selection of a channel model here. Okay, so we try to understand in this particular topic regarding the effect of the signal characteristics here on the particular channel that we are going to select here, right? Channel model here. So, for understanding this particular topic here, let us consider low pass equivalent signal here. Okay, that is as usually you can see here, SL of t is considered here as a transmitted signal here over the particular channel here. Then corresponding SL of f here, that is nothing but the frequency content here. Okay. So again, equation number 1 and equation 2 are represented with the time domain and the frequency domain functions here. So those are nothing but received signals here, right? RL of t is equal to minus infinity to plus infinity, and whatever the channel response is there here, C of tau colon t and SL of t minus of tau here, and, d tau here. Okay, this is the equation concerned with the received signal here, that is low pass equivalent received signal here, exclusion of what you can say that DT noise here. There is no noise has been added here. So this is a time domain variables here, equation number 1, and equation number 2 is a frequency domain here. Okay, so what we are doing here is we are trying to transmit the digital information here uh, for the channel here by just modulating one basic pulse here. Okay, whose rate is 1 by capital T here. So I think you know the capital T is nothing but our signaling interval here. So this time variant channel is characterized by what you can say that C of f colon t here. That is the transfer function we are having here, which is going to distort our signal which is going to be transmitted here. That is SL of f here. Okay. So let us understand that if this particular signal which is there in the frequency domain here, SL of f, has a bandwidth of W here. Okay, and this W is greater than whatever the coherence bandwidth we are having here, delta fc of the particular channel here, then the channel is said to be frequency selective here. Okay, right. Now now if there is an additional distortion is there due to the time variations in the particular channel here. Okay, so in the received signal strength here, and it is called as a fading here. Okay, additional distortion that is being introduced or caused by the time variation in the received signal strength here is called as a fading here. Okay, there are two types of distortion that are being discussed here. One is frequency selective here, another one is a fading here. Okay, frequency selective is nothing but here it depends on this multipath spread here. Okay, or you can say that delta fc here, the particular channel here, relative to the transmitted signal bandwidth W here. Okay, based on that one we can define here if capital W, that is bandwidth of the signal that has been transmitted, is much greater than the coherence bandwidth, means it is frequency selective here. Now what is this fading here? Fading depends on the time variation here. Okay, time variation that has been caused in the channel here. Okay, and also it depends on what you can say that this coherence time or the Doppler spread here. Okay, that is beta d here. Now we try to understand this effect of the channel here on the transmitted signal here, right? Okay, what is transmitted signal we are having here? SL of t. Okay, which is a function of signal bandwidth and the signal duration here. That is capital W, and what you can say that we can consider signal interval also here. That is capital T here. It is a function of. Okay. Now, if the particular bandwidth of the signal pulse is W is there, okay, which is approximately equal to 1 by capital T here, right? Okay. Now, if the signal bandwidth W is much more, okay, lesser, or you can say smaller than the coherence bandwidth of the particular channel here, then the channel is called as a frequency non-selective channel here. right? That is FSN here. In the previous thing we have discussed regarding frequency selective here, where signal bandwidth or transmitted signal bandwidth W is much more greater than the coherence bandwidth of the channel here. That is delta FC. Okay, now the received signal is the transmitted signal here. Okay, uh, which is been multiplied by some by a complex valued random process here, okay, which represents the time variation characteristics of the channel here. Okay, the multipath components in the received are not resolvable here. Okay, so here what we try to understand is regarding the slow feeding channel here. Now, if you consider that signal bandwidth is W, okay, which satisfies the condition as W should be less than or equal to coherence bandwidth, and the signal interval capital T, which is less than the coherence time here, okay, that is delta C, and the channel attenuation and the phase shift are fixed here. Okay, whatever the attenuation that has been there in the channel and whatever the phase shift we are having in the particular channel is fixed here for the at least, okay, one signal interval, then the channel is called slow feeding channel here. Okay, right. Now uh, so how much the signal, or you can say how much the channel is going to be fed in the frequency non-selective channel is how exactly we're going to determine here. It is being determined based on the correlation functions here, or you can say that Doppler power spectrum here. Okay, also certain parameters are there here like delta T, see that is coherence time here, and also BD here, Doppler spread here. Okay, can be used to characterize the rapidity of the fading here. How much a channel has been fed, based on these parameters we can define either the correlation function here or the Doppler power spectrum, okay, coherence time or Doppler spread here. Okay, now now if the W, that is transmitted signal bandwidth, is approximately equal to 1 by capital T, or you can say it is inversely proportional to the T here, then the condition of the channel, channel B frequency and slow fading here, okay, it will be slow fading. Then the product of whatever the TM is there and the BD is there here must satisfy the following condition here. That is TM into BD should be less than 1 here. This particular TM into BD is nothing but here, it is the spread factor of the channel here. Okay, the product of TM into BD, okay, is nothing but a spread spectrum of the channel here. Now if the spread factor of the particular channel is less than 1 here, then we can understand that the particular channel is under spread here. Now if this particular product value is more than or greater than 1 here, what we can understand is our channel is over spread here. Okay, this is how I can explain, or this is how we can understand regarding the signal characteristics here. Okay, on the particular channel model here, right? Now now let us move on to the next topic here, that is binary signaling over frequency non-selective relay feeding channel here. Okay, now in this particular topic here, what we are trying to understand is there is a frequency non-selective channel is there, that is FSN is there here. Okay, so because of this FSN there is something called as a multiplicative distortion is there regarding the transmitted signal here. What is this multiplicative distortion? Let us consider distortion as a noise here. Okay, this noise is due to random scattering here, okay, in the material here, right? That is multiplicative distortion you can consider here. Okay, random scattering of any kind of a distortion can be considered as a multiplicative distortion of the particular transmitted signal here. Now what is going to happen here, the channel will be fading very slowly here. Okay, this implies that, okay, that the multiplication process may be degraded here at a constant duration, at least for one signal interval here. Okay, now the transmitted signal is given by this SL of T here, and the received signal is given by RL of T here. You can see in this equation number 1 here. Okay, now as the channel is going to fade slowly here, what is going to happen? The phase of the particular signal will be shifting here. Okay, and this particular phase can be estimated from the received signal here without what you can say error here by coherent detection here. That means the receiver is aware of what kind of a signal is going to be transmitted from the transmitter here. Okay, that too passing through what you can, there is one filter called as matched filter here, only in the case of what you can say that binary PSK here. Okay, so we are trying to determine the probability of error here. Okay, and this is done, okay, for fixed channel here, remember. Okay, now what is the error rate that for a binary PSK as a function of received signal to noise ratio, that is gamma b here, you can see in this particular equation number 2 here. Okay, now now, if at all we consider the error probabilities here, what is alpha here? Alpha error probabilities alpha one alpha is random. They have written, right. What is this alpha? Alpha is nothing but here. It is a Rayleigh distribution here. Okay, random variable is there, which is Rayleigh distributed here, as we discussed the previous topic here. Then we'll try to find out the average here. Okay, average over the particular signal to noise ratio here. Okay, then this equation 3 is going to be resulting here. Now, let us consider this Rayleigh fading here, where alpha is the Rayleigh distributed here, and alpha square is nothing but here chi-square probability distribution here, with the 2 degrees of freedom here, right? Okay, now this signal to noise ratio gamma b is also considered as a chi-square distributed here. Okay, so if that is the case here, how can we write the PDF here? Okay, in the Rayleigh fading here of the signal to noise ratio, right? So probability of a signal to noise ratio b is given by 1 divided by gamma b over the bar here, e raised to minus yb divided by, you can say that yb bar here, that is nothing but gamma here. Okay, so this is how the average signal to noise ratio can be defined here, as you can see in equation number 4 here. Okay, signal is given as a EB here, the noise is a naught here, and expectation of alpha square. Alpha square is nothing but a chi-square probability distribution here. Okay, now let us try to substitute the equation number 4 that we have here in the equation number 3, and if at all we carry out the integration here, then we will be having this result here. Okay, that is nothing but equation number 5 here. Okay, this is the estimation, what you can say that of the channel phase shift here. Phi is noiseless and performance achievable in the presence of Rayleigh fading here. Okay, so this is how we can understand, or we can replicate here, or try to understand regarding this frequency non-selective fading channel here, that to Rayleigh fading channel here, binary signaling here, right?